The following presentation is part of the Technology and the Corporation Conference Series, sponsored by MIT's Industrial Liaison Program.
Today I'd like to share with you a technological adventure that I had the chance to do on the field of sustainable materials extraction. And I think it's particularly relevant for Brazil, speaking about minerals and how to capitalize on their value. I'll do that by going first through a brief introduction and a context for the research that we've made, and then I'll move on into the specific of the fertilizer and potash situation and the role of technology to do that, before delving into the project we've done at MIT, which is about feldspar for fertilizer, and ending up with some opportunities that we are pushing forward in the field of minerals extraction. We've heard yesterday a lot about the challenge of 9 billion people by 2050, and it's very interesting to look at the data in the last 30 years, where all the index that are shown on that graph refer to the 1980 data. And if you look at, indeed, in the last 30 years, we've had a large increase in population. This is going to continue to move on. And what is interesting is, as we've heard yesterday, is that the GDP of the planet also went up. So on average, people are getting wealthier as they get more and more numerous. The last curve that is on that graph refers to the materials demand. I'm sure you can do that with many other commodities, but it's very under-regarded, the fact that materials demand is actually increasing as you get wealthier and wealthier. An interesting aspect that comes along with the wealth of people is the need for food. And here the data from the Academy of Science in the United States show us that if you see your GDP per person increasing, these are data in $1990 per year, you actually get along that curve, which kind of immediately tells you you're going to consume more and more calorie as you're getting wealthier and wealthier. So this is creating some interesting challenges for the 9 billion people that we will have by 2050, and it's actually, I think, offering some good opportunities. Out of these opportunities, we need to look at materials. These data, again, are from the same institute, the CRE Institute, where you can see in billion of tons how much materials were consumed in 1980, and the green curve that I showed you before basically is exploited here into various materials. Among materials, clearly, biomass is increasing. The amount of fossil materials is increasing as well. When we say fossil, we think also about the carbochemistry, the ammonia generation. But what is really surprising as a metallurgist is how much the demand in metals and minerals has increased. Minerals, where we're speaking about sand to make cement, calcium oxide, but also potassium chloride and phosphate. In terms of metal, we're speaking about iron, clearly, aluminum and copper. And what is really remarkable is that if you want to do something in terms of materials demand and have a field of growth, you see that metals and minerals are the fastest growing market in terms of materials demand. This is a perfect opportunity for new business in growing the wealth of countries who have access to these resources, but there is a challenge. The challenge is clearly the environmental impacts, and here I gathered some data which are related to first the United States. This is showing you the greenhouse gases emissions for materials in 2013. These data are from the Environmental Protection Agency, where you can see that the share of metals and minerals in terms of greenhouse gases is more than 50% of the overall materials emissions. It doesn't stop only with CO2 emissions. You can look at acidification potentials, which is shown here for the main metals that we are speaking about, where you can see that the equivalent SO2 per ton of metal is also very large, and the impact on the environment is actually pretty significant. So here we have a very classical paradox where we see more and more demand and opportunities for materials, but at the same time we have an environmental impact which is not acceptable for the 21st century. So what is the situation of Brazil in this landscape? Well, we know about the iron ore. Brazil is one of the leaders in the world in terms of providing the iron that's going to be used for the development of mankind. But what is shipped is actually not iron. What is shipped is iron ore. We have here the example of a boat of 250,000 tons of iron ore, which only 60% to 70% is actually made of the value, which is the iron metal that we will use down the road. What are the consequences of that? Well, you can compare the value of the raw materials in 2010, where basically a ton of iron ore was dealing for $150 per ton, while steel was around $800 per ton. Nowadays, with the slower development of the steel demand and basically a kind of a tension in terms of economical development, we can see that the value of the iron ore decreased by 50%. So suddenly, a leadership in terms of tonnage doesn't mean anymore a very high revenue compared to the steel makers, which have been, seeing a drastic difference by 20%, but clearly we are not speaking of the same order of magnitude. So Brazil has a global leader position, but we can see that because it's exporting iron ore instead of exporting iron, it's actually very dependent on the iron ore customer. What is the situation in food production? Well, here the news is even better. This map shows you the production of various grains, corn, oilseed and soybean, and the greener is the map, basically the larger you are. And we know that for oilseed and soybean, Brazil is one of the number one. It's number one in sugarcane in overproduction. What comes with food production? What comes with exportation of corn? Well, here is the true mining aspects of food production. This is the amount of nutrient in pound per unit, the units are here, that you need to add when you ship these food products. So you can see that if you are harvesting sugarcane, you need to provide 3.5 pounds per ton of sugarcane of potassium that you need to put back into the soil if the year after you want to be able to continue to grow food. So there is a clear sustainability issue. In order to sustain your leadership, you need to actually maintain the quality of the land. So Brazil has exceptional land, exceptional rain season in some of the regions, but this rely on fertilizers. So what is the situation of Brazil for fertilizers? Here the news is slightly less optimistic. This map is a very complex map, but you can see that most of the arrows in terms of the purple color, which are potassium chloride, the fertilizer that Brazil is actually needed, are going toward Brazil. In 2011, 93% of the potash needs were imports, around 8 million tons of potash, which is the equivalent unit to count how much potassium you import. This potash is actually subject to large variations in prices. Maybe you remember the food crisis around 2008, which led to a spectacular increase in the ton of potash price, which went from around $100 per ton up to $900 per ton. And you can see that things have got better in terms of world market, but experts are all agreeing that this number will never go back to the regional number before the beginning of the crisis. What is happening is that potash, in terms of imports, is a northern hemisphere product. It contains 60% potash and, for example, comes from Canada. We can look at the situation in Canada, where basically the country is mining 1 kilometer deep into the ground to get access to soluble salts deposit, which will actually be the source of the potash. So when you want to think about building such an operation, not only do you need to find a salt deposit, but then you need to invest in at least 2 shafts. 1 shaft to bring down the machines, bring down the people, and 1 shaft to bring up the raw materials that you can finally export. On top of this, on the ground here, there are other operations that are needed, and at the end of the day, you're finally able to make a product which is 60% potash. What is interesting in these developments is that the capital cost to actually develop a new potash mine today, respecting the environment and the regulations, is around $3,000 per ton of potash per year. All this to make a product which cost is around $150 per ton of potash. These developments in Canada, you have similar developments in Russia and former USSR, and these have been done in the 50s, 70s, and 60s and are still in operation. So nowadays, these companies have actually amortized their capital investment and can actually ship potash at this price point. What is the situation in Brazil? Why can't we replicate this very expensive cost model in Brazil? Well, there is one reason for that, is that most of the future development of food actually in the world will happen in Brazil. The Cerrado region, which is highlighted here in gray, represent 5% of the world available arable land, which is going to be able to match the requirements for 9 billion people. It has been projected by 2020, 11 million hectares are going to be developed in Cerrado, which represent half of this capacity. Nowadays, there is already 2 million tons of potash that are consumed in this region, and you can anticipate that this demand is going to be multiplied by a factor 5. What is the other situation and specificity of this region? And here you have to call on the expertise of Brazilian government agency or research agency, Embrapa, who knows extremely well what's happening in these soils. These soils are very different. These soils are actually more than 1 million years old compared to 10,000 years old for United States, between 1,000 and 10,000 years old in Europe. What happened around after 1 million years of weathering? Well, basically you have leached all the nutrients and you are left behind with the most refractory element, including iron and aluminum. This gives the color that we know pretty well. The red clay that you can see is actually made of iron and aluminum, which are staying in the material. What is the outcome of this deep leaching is that if you add potassium cations to this system, they will not be retained. They will actually leach away at the first raining seasons, which means that it's very difficult to actually provide the good amount of fertilizer for a crop to grow. What is the outcome of this is that Embrapa knows nowadays that potassium chloride, which I showed you, is a Northern Hemisphere product, which is mined in the Northern Hemisphere and actually has been developed historically for Northern Hemisphere soils, is actually not the most efficient potassium source for the Cerrado region. There is another issue with the development of the Cerrado soil, as you can see on that map, is that it's located very far inland. It's very far from the ports, and as you may know, the infrastructure in Brazil actually add another burden to the farmers who want to import potash from Canada. It's estimated that it's around $100 per ton of material to transport from one of these ports located here to this agricultural region. So we can see that the raw materials are not available, the materials that is available is not relevant for the Cerrado soil, and you have an infrastructure problem. We are very in presence of a very typical technological framework which we like to tackle in my laboratory. Indeed, this existing materials processing paradigm is very classical of commodities extraction based on minerals. What happens is that you have a single feed. You decide that you want to work with soluble salts. You have also a single product. You design it so that it works very well for a single market. At that time, it was the Northern Hemisphere soil. It was the US soils, the European soils, in Germany, in France, and in other countries. Now, once you know that, you define basically a technology which makes you very efficient to provide the customer needs, but when another customer, like for example Brazil, comes to the party, there is actually nobody to help you. Second of all, because of the size, you're going to be very sensitive to global market. And size matters. While we're speaking about commodities, and in order to guarantee the quality of your product from this feed, you actually need to add multiple steps. We've seen the shaft. I didn't show you the various steps to crystallize potassium versus sodium chloride. This is a fantastic technological development. Engineers are very good at doing this. However, it comes out with a very high capital cost. So what is the consequences of a high capital cost? Well, you need high volume to be cost efficient. And this is exactly the scenario that we end up with in the potash system, but you can translate this to other commodities. Finally, there is a last aspect, is that here we consider that all soils are equal. Northern Hemisphere, tropical soils, these are all the same. Well, at the end of the day, this is not really what we call a green chemistry approach. This is not very sustainable. Well, on one side, there are some issues with leaching of these salts which accumulate in rivers, but there is also an issue of waste. The farmer who's buying 60% of potash today, we estimate that there is half of the potash, or 30% of the potash, which actually leach immediately and is not efficient. So this is wasting minerals of high value. you can see that we need to rethink this framework, and that's where materials processing is very efficient. And we would like to propose a new paradigm where basically, what if we found new technologies that may be compatible with different types of raw materials? What if we were to develop a model where we have a technology that makes much lower capital cost so that you can implement it in regions which are not the traditional regions where you develop materials processing? Finally, if we do a green chemistry approach, maybe we can also be compatible with lower capital cost and go in regions which are not developed today in terms of materials extraction. How would you do that? That's what I want to share with you today in the theme of potash. How would you do that? Well, you will first have to listen. The first thing you have to do is to understand the geological and mining realities. And we've been fortunate enough to meet a Brazilian company which is called Terrativa, which is an independent mining development company that has been doing the job for us. Terrativa you may have heard of because they are the one responsible for the new iron ore project developed by Manabi in the iron ore quadrangle in Minerais, which has been very successful as raising funds and is going to deliver 25 million tons of iron ore pellet quality feed per year for several years. Now, Terrativa has continued to be active after this project, looking for nickel, copper, and gold, but more specifically, looking for potassium. What they did is that they actually came to us in November 2011, and they basically said the following. We have found a resource of potash, which is more than 15% potassium oxide, and is present in very high-quality rocks. These rocks are made mainly of feldspar. You can see on this picture, anything that is blue, white, gray or black is actually a potassium feldspar. This is a thin section, a petrographic section, as we say in geology. And the only impurities that you can see here are the green material, which is an iron magnesium silicate. Well, that's very interesting from Terrativa's standpoint is that they find out, for example, in Pernambuco, this is near the city of Triunfo, that it's actually pretty easy to mine. This would be a quarry type of mining, very different from the deep sea mining, deep salt mining that I showed before. What is remarkable and what makes sense from a mining perspective is that there are large quantities of these potash-rich silicates that are easy to mine. So that already makes a case for thinking about, now that we have these resources which are fairly rich, how can we move forward? More interestingly, Terrativa also did the work to find out inadequations between where are the farmers, where is the Cerrado region, and where are the mine products. And they've done quite an amazing job in finding different regions and different mines all over the Cerrado region that basically allow to avoid the transportation problem and reduce the infrastructure cost for providing potash to the farmers. Altogether, they demonstrated availability of huge amount of potash. But at the end of the day, there are other criteria. There is the environment, there is the availability of transportation, which ended up defining around 200 million tons of potash in strategic locations in the Cerrado soil. This is a perfect story of how Brazil is an amazing opportunity for minerals and materials processing. However, there's still another problem, is that once you have these resources, you need to understand what the customer wants. You need to understand what are the end users' specifications. And this is where Embrapa was actually already working on that problem. Actually, Dr. Martins here is a specialist in the Cerrado soils. And basically, when the people from Terrativa came with this cyanide material, he basically told them very quickly that there is not that much of the potash that is here that will dissolve and be immediately available for the crops to grow. At a high level, potassium dissolves too slowly from the raw feldspar material. So this is where they actually start to ask themselves, well, mostly the mining company was asking this question, well, is there any economically and environmentally viable processes that would allow us to produce the desired fertilizer for the Cerrado soils? This is where we came to me at MIT in order to find a way to basically make all these resources, which have a high value at the beginning, but a value that is entrapped in the mineral. So what we did is, 3 months after we met in November and he explained our problem, we basically got a project together where we have direct funding from Terrativa on multiple years at a pretty high level of funding. Why did we require this high level of funding? Well, because we're dealing about a huge problem. We're speaking about millions of tons of materials for a new process, a new raw materials to make a new product. So this money allows us to actually bring to MIT a team of professional researchers, fresh PhD, people with experience in different fields, as well as allow us to buy equipment, to travel together. We went to Brazil several times. We had several meetings, actually all over the world, to understand really the situation of the fertilizer and basically the needs of the Brazilian soil. So this is a breakdown of how the costs look like. I think this is pretty interesting to look at. Most of the money went to people, but as I said, we had some dedicated equipments, for example, to make sure we can accelerate the pace of discovery, as well as some money to bring experts and have different seminars and conferences. What did we offer to do on these 3 years is a very comprehensive approach to the problem. There are some raw materials work, there is some characterization of the cyanide leaching, trying to understand how can we predict the performance in the soil versus the performance in the laboratory. But today I want to focus on one aspect which I think is more relevant, which is the processing options. What process did we develop to actually match the need of the Cerrado soil? We learned this from history. We've actually published a review that is reviewing the development in potash since 1700. It's a very interesting history between the relationship between Germany, France, England, the United States later on, and then Russia. It's a very interesting commodity story, which ended up showing us that people have been thinking about that since the beginning of the 19th century. The first patent in the United States is about a process to extract potassium from feldspar. In 1907, at MIT, people were studying the extraction and production of potash from feldspar. From this, we learned a lot of things. We learned that people have been trying to apply conventional approach to this chemistry problem. This is the K-feldspar, where the potassium is actually the blue dot, the blue spheres that you have here, and everything else is an aluminum silicon oxide structure. If you go in weight percent, you will find out that the easiest thing the most economical thing to tackle is to try to remove alumina and potash. And to do that, basic chemistry, these are basic oxides, you use a basic solvent. In that case, you will need a base, sodium hydroxide, for example, high temperature, high pressure. What chemists wants to do here is to destroy completely this network, to separate in beans, separates potassium on one side, aluminum on the other side, and silicon on the other side, which means that you will have to reprecipitate selectively the salt you are interested in. There is one example of this process. It's called the Bayer process. It's the process from which we extract 100% of alumina today, and I don't want to go into the details of the environmental and the capital costs of this process, which are very well known. What would be a more sustainable approach for the specific potash problem? The most sustainable approach is to listen to what agronomists are telling us. They are telling us that we need to make potash available, that aluminum is not a problem. The Cerrado soil is already full of aluminum. The only problem is to make sure that aluminum doesn't dissolve as an aluminum ion. There's a pH problem. You need a pH higher than 3. And finally, silica. Silica is a very good thing for these soils. I just explained that most of the silica got dissolved over a million years, and most of the best performing soils have a high amount of silica. So fundamentally, adding silica to the soil is a good idea. Now, on the other side, that was the specifications from the users. You can imagine that the mining company tells us a very different story. They say you're not allowed to dilute the potash value. Don't add anything, please. Then they say we don't want any waste, we don't have any problem, we want no water consumption, and we want no energy consumption. I'm sure many people have seen this type of experience where you have very different feedback from your colleagues. So what we did is we tried to scratch our head, and we find out that a hydrothermal treatment would work, where we basically add something that is beneficial to the soil, calcium oxide. Calcium is beneficial for this very acidic soil because it neutralizes the acidity. Now, on the other end, we did a joint milling together, and we did a pretty mild hydrothermal treatment. 200 degrees Celsius, around 10 bar, and then we dry everything and we have a hydrocyanide which kept most of the value. There is a 10% dilution in the potassium content. So we moved from this rock, which you may have seen actually in different area because we use it to make buildings and other things, into this material which has a very different structure. The leaching performance are very good. This is the performance after 24 hours of the original material. We see that we've been able to increase by 50 times more the amount of potassium that can be released. And this actually all came from material science and chemistry. If you look at the structure at the atom level, this is transmission electron microscope, we can see actually two different phases that are formed. One phase, as you can see here, seems to have no atomic arrangement. This is an amorphous phase. This is actually a gel that contains the potassium that will be available later on. The other phase, which you can really see here, are these needles, which is actually a very crystalline phase. You can even see the atomic ordering of the atoms, which is very characteristic of the crystalline phase. Why is this important? Because actually this crystalline phase is forming a calcium silicate in the name of tobermorite. Tobermorite is a very stable material and has actually some interesting capacity to interact with soil, and at the end of the day it allows us to avoid overliming. Because, you know, as anyone does cooking or soil, if you grow your own crops, you know that if you add too much of something, there is always there's no feedback mechanism, and usually the crop is dying. So there might be a problem with calcium, which we've been able to fix by controlling this phase formation and allowing to sequester the calcium that we add into this crystalline phase. Now, what is very interesting is that since potassium feldspar constitute maybe 50% of all soils in the world, they have some potassium feldspar. It's available all over the world. You have it in the Boston area, you have it in China, you have it in Europe. And interestingly enough, we've been allowed to operate with rocks from China. China has the same problem as Brazil in terms of imports of potassium. And we demonstrated that the performance of the process, the performance of chemistry, are independent on the origin of the potassium feldspar that you may have. In terms of scale-up, the process is fairly simple. We've been able to do some scale-up events in our laboratory, and then at some point we moved to a pilot plant facility in the United States in order to make enough amount of material to be tested. Because that's the next step that I want to share, is that Embrapa, this Brazilian agency, has actually been testing this material in a crop test. So you can see here corn crops which are grown in pots. And the outcome that you can see here, where you have something that doesn't contain potash, this contains potassium chloride that you can import from Canada. And here is the hydrocyanide material that I showed you that we developed at MIT. And Embrapa is extremely happy with the performance of the material. They really think that this is going to be a fertilizer approved, and we have a pretty good feedback from their research work on this material. What is the next step? Well, you know that agricultural people and farmers are very conservative. They don't want to put things in the field that may harm the next year of yield and crop production. So Embrapa is actually going to start large scale, right? This is 20 meters between the two rows that you can see here. Large-scale tests to actually validate over different harvesting season, over different crop recovery, that the material is performing according to what we've seen in the pot test that I just presented before. So what will be the next idea on this project? This is what we're doing right now at MIT, is that at that stage today, Embrapa is pretty confident about the performance of the process that I showed you and the materials that I just presented. However, the resources are still here, and there's more than what Cerrado will ever need in terms of feeds. So what we're trying to do now is to develop another process to now concentrate potash. The idea would be to be able to transform some of these silicate materials into a traditional salt, so that we can feed, for example, the northern hemisphere, who has been exploited for so many years, the deep sea mining. So I cannot disclose too many things on these aspects because this is pretty recent, and we want to make sure we protect that. But what you can see here is, again, a cross-section of a feldspar where the bottom here is really unreacted. Without any problem, you see an interface here which is pretty black, and here is another phase that has been formed. And to our surprise, at a temperature very reasonable, between 300 and 800 degrees Celsius, we've been actually able to form a new phase located here, which has more than 58% of potash, from something that at the beginning was 15%. We've been actually to find something to substitute the potassium in the potassium feldspar by more than 90%. When you do an analytical analysis, an elemental analysis on this layer, which is around 100 microns, you find that you've been able to extract 90% of the material. So we're very excited about this approach because this would allow to also develop some salts, which sometimes are very important for farmers in some special conditions. Why has this been possible? I think I've insisted quite a lot in the size of this project and how much autonomy was given to us by this mining company. And the way we solved this problem was not by hiring people who have a PhD in soil science, with all respects to what these people are doing. We actually hired people that were motivated by the sustainability issue, by the needs from Brazil, people that had an open mind, and most of the people were international. So we met, as I said several times. This is a World Congress in Rio that was held in the last fall. You can see here our chemical engineer from Italy who did his PhD in Australia in solvent extraction. This lady here is from France. She has a degree in chemical engineering, and she actually did her study in titanium oxide surface properties. Down here, we see our collaborators from United Kingdom, Professor Manning, who's in Newcastle, who's really someone, an expert in geology and soil processing for environmental issues. We've been able to hire a geologist because you can imagine, at the beginning, someone comes to you. I'm personally from the iron business, right? I'm someone from steel industry. I know iron ore very well, but if you come with some new raw materials, I don't have all the knowledge in geology to understand everything. So what do? Well, you hire an expert in geology. She got her PhD from Indiana University, and she actually teaches us to look at the material. She taught us how to use fin section. She taught us how to use petrography to understand what will be the interactions between fluids and salts and other issues. We had also a brilliant chemist who's now working with 3M, who's an expert in silicate. Dr. Scorina was an expert in cement. Maybe some of you are familiar with tobermorite, but tobermorite is actually the phase that is formed in the aging of cement. And finally, we have a last chemical engineer from China, Dr. Li, who was actually involved in the leaching experiments and developing the chemical engineering aspect of it. So you can see we have someone from China, from Russia, from the United States, from Italy. We were working with people from Brazil. Here are all the lead engineers from Terrativa, which are located here. This is how things get moving at MIT. We've been able to attract these people to face this very difficult problem and to work very hardly so that in 1 year and a half, we were able to actually propose the first sample to be tested by Embrapa. And I think this is illustrating pretty well what we are allowed to do at MIT thanks to a very nice collaboration with, as you can see, right, people from the mining company are here everywhere and they met with us very often, being open-minded to our ideas, but also reminding us about the economical constraints and the environmental constraints. In summary, you have fantastic resources in Brazil, not only for potash, but for everything. But for potash, you have potassium feldspar, which have a very high potash content, and they are available. They are easy to mine. There are not that many environmental issues with their mining. What we've done at MIT is we have developed a hydrothermal approach to allow to cope with both the economical requirements. Remember, we're speaking about something that at the end is $150 per ton, as well as the environmental reality of potash. And here I'm speaking about the specificity of the soil in the Cerrado region. The process is not traditional. We're not trying to destroy and get the value of only potash. We're trying to keep everything together to avoid generating waste and to guarantee we make the best use of the minerals that are available. So we actually transform the feldspar to accelerate the rate of potassium leaching and the amount of available potassium. This allows us to keep the minerals that are in the product, which I showed you, are very beneficial ultimately in the long term for the performance of the Cerrado soils. I mentioned this at the beginning, and I just said to you that originally I worked in the iron and steel industry, so I need to mention something about metals, in particular in the context of Brazil. So I already mentioned the fact that Brazil is #1 in exportation of iron ore, and that the value is not in the oxygen, the value is not in the water that you're transporting, but the value is in the iron that you're making. And here, the technological paradigm is very well known. Anyone in the steel industry will tell you that to make steel, you need carbon. You're going to use a blast furnace, which needs coke oven, which needs sintering, which actually need a step where you remove the excess of carbon that you've added before. And we know the environmental consequences of that. The CO2 emissions and other issues in the coke plant, in the sintering plant, and in the BOF. So what would be the new paradigm? How can we actually change this in order to allow to develop new technologies that match the realities of the requirement in the 21st century? Well, that's what we do in my laboratory, and I want to very quickly explain what we're doing in the field of metals extraction. The first process that we've developed is actually taking iron oxide particles, very fine iron oxide particles, like the dust you can see on the road of Belo Horizonte. You take that and you can actually do an electroforming process. You can take these particles and at very low temperature actually make a shape. For example, you can make round tubes directly almost at room temperature made of high purity iron. If you don't want to make shape, if you want to match the existing physical metallurgy of liquid processing, we've already also developed another technique that works at very high temperature, that works at 1600 degrees Celsius. Why 1600 degrees Celsius? Because that's the melting point of pure iron, 1535 degrees Celsius. And we've actually been able to build a first pilot cell, which is actually producing 100 pounds of liquid metal per day. As you can see here, it's an electrochemical process, the same concept as this one, but now we are able to tap periodically the liquid metal that we are forming while we are allowed to feed periodically the oxide feed that we're speaking about. This process for oxides actually was developed initially to make manganese, or more specifically ferromanganese. We've actually demonstrated it for iron, we've demonstrated for nickel, we've demonstrated it for chromium, and we are working in the demonstration of its operability to make titanium and rare earth elements. You're going to say, how come they can do that with the same technology? Well, it's because we've designed it to take into account the feed. We're using an oxide feed, and we're actually using an oxide system to dissolve the feed into the oxide and selectively get whatever metal we are interested in. As you know, the second biggest nature or compound for raw materials on the earth in terms of metals are sulfides. Copper, for example, comes from sulfides. Most of the rare elements that you have in your smartphone are actually byproduct of copper extraction from sulfides. The platinum group elements come from sulfides. And we've actually developed, following a pretty much the same idea that like dissolves like, we've developed basically a process where we are using directly a liquid sulfide, a molten sulfide system, to feed some sulfide minerals, for example, chalcocite, for example, tin sulfides or platinum sulfides, and we're able, using electrolysis, to directly make sulfur on the anode. You don't see the anode is on the other side here, but we make S2 instead of making SO2, for those of you who are familiar with metallurgy. And on the other electrode, we actually make liquid copper, in that case, of very high purity. So we've been able, in a single step, to actually process the sulfide minerals without any acidification potential with sulfur, which is a pretty convenient byproduct. You can make bricks of sulfur and you can transport it. You can burn it later on if you want. You can make fertilizer out of sulfur. So this is a very interesting approach, which shows that if you change the technical paradigm, you can actually think of changing the way we use the value in the raw materials that you have available, for example, in Brazil. With this, I'd like to acknowledge clearly the sponsorship of Terrativa, who have helped us to not only work on the field of sustainability of fertilizer, but also allowed us to very well understand the issues in Brazil and the advantages in Brazil. We've been traveling all over the state. We've been to Pernambuco, to Recife, Triunfo, Belo Horizonte. You can name many places where we've been to try to understand how this country is developing and what are the fantastic opportunities available. I'd like to thank the support of MIT Industrial Liaison Program for putting this conference together and helping to make relationship with Brazilian companies. And finally, all this is not possible, as you've seen, without the fantastic people who are working with us. This includes the postdoc that I mentioned, but of course also my graduate students who are working on, for example, the sulfide processing, and who are all very excited in proposing new technologies that will allow, for example, Brazil to become not only more rich thanks to the minerals that they have, but also be sustainable to match the 21st century challenges. Thank you for your attention.